One is your boiler pressure and one is your condenser pressure. Okay, by increasing the boiler pressure, so we can increase the efficiency. On the other hand, by reducing the condenser pressure, we can increase the efficiency of steam power plant. You remember we are having basically four parts. One is a boiler, one is condenser, one is a pump. Okay, so by reducing the condenser pressure, we can increase the efficiency, or by increasing the boiler pressure, we can increase the thermal efficiency of your steam power plant. Okay, now today first I'll make the comparison between Carnot cycle and your Rankine cycle. First, in one TS diagram, how we are going to represent. Sometime they used to ask, compare the Rankine cycle and the Carnot cycle. Okay, cycle and your Carnot cycle. Okay, so hope all of you are seeing the contents on the diagram. Okay, there is a superimposed TS diagram. Okay, here we are representing both cycles. Okay, as I said, in the Carnot cycle, we are having the two constant temperature process and followed by two reversible adiabatic process. Okay, you see the diagram. This is called as saturation curve. Already you know in Mollier chart. Okay, this is a saturated curve. So above saturated curve, we are having the superheated steam, and whatever the reason below this one, it indicates your the mixture of liquid and vapor region. Okay, so one is liquid plus vapor region. The above this point is a superheated zone, and we are having the 2 points. Okay, one is a critical point and one is your triple point. Already we studied in basic thermodynamics. Critical point is one where it is very difficult to distinguish between your vapor phase and the liquid phase, and all the liquid is directly converted into vapor without supplying any Okay, here in this diagram, first you see the points 1, 2, 5, 4 is your Carnot cycle. Okay, so this you remember, this is a TS diagram, not a PV diagram. So in case of Carnot cycle, we are having four processes. 1 to 2 is your isentropic expansion. 2 to 5 is your constant temperature heat rejection. 5 to 4 is your isentropic compression, and 4 to 1 is your the constant temperature heat addition. This is the Carnot cycle. Cycle 1, 2, 5, 4. You see the diagram 1, 2, 5, 4 your Carnot cycle. It is not PV diagram. Remember, this is a TS diagram. Okay, 1 to 2 is your isentropic expansion. 2 to 5 is your isothermal heat rejection. 5 to 4 is your isentropic compression, and 4 to 1 is your isothermal heat addition. Okay, this is the area under curve 1, 2, 5, 4 represent whatever the amount of the heat transferred or rejected during the Carnot cycle. On the other hand, you see the points 1, 2, 3, 4, 1 is your 1, 2, 3, 4, 1. Okay, is your Rankine cycle. Very simple, because we are having the curve in Rankine cycle. We are not getting the curve in Carnot cycle. Okay, 1, 2, 5, 4 is your Carnot cycle. 1, 2, 3, 4, 1 is your the Rankine cycle. Okay, the change in process 3 to 4. Okay, but we don't have the process 3 to 4 in Carnot cycle. We are having exactly isentropic compression, but here in case of Rankine cycle, we are having the one intermediate point called as the 4. So where the preheating takes place between 3 to 4. Okay, 1, 2, 3, 4, 1 is your Rankine cycle. Okay, now you make the area into different parts. Okay, we can call the 1, 2, 5, 4. It is a rectangle. You call this part as C. Okay, the portion 3, 4, 5, you call that portion as B, and this portion you call it as E, and this portion you call it as D. Okay, so what is the heat input? Okay, heat input is same in both the cases. Okay, so the heat, first you see the Carnot cycle. Simple Rankine cycle is 1, 2, 3, 4, 1. Okay, and what about heat input? As I said, the heat input takes place at constant temperature process or isothermal process, that is nothing but your 4 to 1. So the area under 4 to 1 gives the heat input in the Rankine cycle. What is the heat input? So you have to take the area of B, C, D and E. So the whatever the curve under 1 to 4 gives the heat input in the Rankine cycle. So area B plus area C plus area D plus area E. So this is the whatever the heat input in the Rankine cycle. And what about the work done? The work done is your the P plus C. Okay, work done. So we'll get in a PV diagram. So the whatever B plus C gives the area. Okay, you mainly concentrate on heat input. And suppose if it is Carnot cycle, what is the area under curve 4 to 1 is you have to take only C plus D. Okay, because 1, 2, 5, 4 is your Carnot cycle. So the heat input in the cycle is only the C plus D. Okay, so comparing this one, the heat input will be more in case of Rankine cycle because the heat input is B plus C plus D and E. It is obviously more than the area under C plus D. Okay, comparing the Carnot cycle and Rankine cycle, because of the more heat input in the Rankine cycle, so you'll get the higher thermal efficiency. You remember, as the heat input increases, so the work done will be more. As the work done will be more, you will get the more cycle efficiency. Hence, the heat input is more. You see the area of B, C, D and E together, it is more than that of area C plus D. Hence, the area under 4, 1 is more in case of Rankine cycle. Rankine cycle is 1, 2, 3, 4, 1. Hence, the heat input will be more in case of Rankine cycle compared to Carnot cycle. Hence, we'll have the higher efficiency in the Rankine cycle. Okay, so because of this heat input. Okay, sometimes they used to ask compare between Rankine cycle and Carnot cycle in one TS diagram. That's why first you have to draw this curve and then you have to represent point 1. You draw vertical line, then 2 to 3. First you draw the Rankine cycle, then 4 to 5. Just you draw one line and then mark that point as 5. Okay, like that you have to represent. And two more things we studied. One is boiler pressure. Okay, P1 equals to P4. That is called as boiler pressure. On the other hand, we are having the values of P2, P5 and P3 are same. These are called as condenser pressure. You remember, P1 is boiler pressure and P2 is your condenser pressure. Okay, so comparing this diagram, we can say that the heat input is more in case of Rankine cycle. Hence, the efficiency will be more in case of Rankine cycle. Okay, and in today's class, I'll explain the one important concept called as actual vapor power cycle. Whatever we studied till now is of ideal Rankine cycle. So how you studied the actual turbine and actual compressor efficiency in case of gas turbine chapter, here also we are going to study the actual vapor power cycle. You studied actual and ideal gas turbine cycle in the module 2. Like that, we are having the ideal and actual vapor power cycles in this module. Okay, before that, first you analyze the TS diagram. Okay, so this is the diagram gives the Rankine cycle. Okay, Rankine cycle. So first I'll tell what are the process comes into picture. Okay, first, so you have to start with point 1, that is 1 means here the enters the turbine, steam enters the turbine at pressure 1. Then 1 to 2 is your whatever the expansion takes place in the turbine. Okay, 1 to 2. First I am explaining the ideal, after that I'll explain the actual. Okay, 1 to 2 is your the ideal expansion in the turbine. Then after the turbine, so it enters into the condenser. Okay, so condenser means what happens, there will be a change in phase takes place from vapor to liquid. So 1 to 2 is your ideal expansion in the turbine. 2 to 3 is your condensation in the condenser, at means it is a heat rejection. 2 to 3 is your heat rejection. Next 3 to 4, you can see the line. 3 to 4 is called as your pump work, means the compression process where the pressure and temperature increases for the process 3 to 4. This is between pump. First one is boiler, next second one is turbine. Okay. Okay, so this is the actual vapor power cycle. 1 to 2 is your ideal expansion in the turbine. 2 to 3 is your the heat rejection in the condenser. 3 to 4 is your pump work. Okay, and then 4 to 5 is your what I said, it is the regeneration. Okay, before entering the water in the boiler, it gets preheated. That is called as regeneration. Then 5 to 6 is your the heat addition at isothermal process, and 6 to 1. Okay, already I explained. I'll explain that chart once, that cycle diagram I'll explain. I'll show once again. Okay, Rankine cycle. Okay, so this is the Rankine cycle. Okay, so we are having basically 4 parts. 1 to 2 is your the expansion in the turbine. 2 to 3 is your condensation, means it is a there will be heat rejection between the process 2 to 3. Then 3 to 4 is our pump work, means whatever the condensate coming out of the condenser, it is gets pumped into the boiler. Okay, and pump and compressor are same. Okay, the work is same. In case of pump, the temperature and pressure increases. In compressor also the temperature and pressure increases. But in case of vapor power cycle, we don't have compressor, but in gas power cycle we are having compressor, we are having pump. Okay, the main function of the pump is to lift or to increase the temperature and pressure. By increasing the pressure, it lifts the condensate from the condenser into the boiler. Okay, we don't have 0.5. Okay, already I explained that 0.5. 0.5 is not there in the diagram because you see the diagram. Okay, 1 to 2 is your the expansion, 2 to 3 is your condensation, 3 to 4 is your pump work, and 4 to 5. Okay, 5 and 6 are not there in the diagram. Okay, you see the diagram, they have shown only 1 2 3 4. Okay, 5 is that here we are having the regenerator. Okay, before passing into the boiler, first the water enters into the regenerator where it gets preheated. Okay, so instead of supplying directly the temperature of the this one cold water to the boiler directly, we have to preheat, thereby increasing the boiler efficiency. Suppose if you supply a very cold water in the boiler, so it takes a lot of time to convert into the steam. Rather than supplying the cold the water, first we have to preheat that air, whatever preheat the water, whatever it is coming out from the pump. Once you preheat, so that it takes less amount of the heat to convert the water into the steam. That's why we are having a part called as regenerator. Okay, that process, you see the diagram, this is called as ideal Rankine cycle. Okay, this is the ideal Rankine cycle. Whatever I am showing, it is on the board, it is ideal Rankine cycle. 1 to 2 is your the ideal expansion in the turbine. 2 to 3 is your the heat rejection in the condenser. 3 to 4 is your pump work, that is the increase in the temperature and pressure, and 4 to 5 is your regeneration work. As I said, 5 and 6 are not there, so that 4 to 5 is your regeneration, means before supplying the water to the boiler, so we have to preheat, we have to supply certain amount of the heat, that is called as regeneration. So that is a small part, that's why it is not shown in the flow diagram. Okay, we have to show only the basic parts. Okay, 4 to 5 is called as regeneration, where the amount of where certain amount of the heat is supplied to the water to increase the temperature. Okay, that feed water is enters into the boiler for further operation. Next, 5 to 6 is your as I said, isothermal, the heat addition. Okay, in order to find out the efficiency, we need two parameters. One is a heat addition and one is a heat rejection. 5 to 6 is your heat addition and 2 to 3 is your heat rejection. 5 to 6 is heat addition at constant temperature process or isothermal process. This is represented by QS. Okay, suppose if you join this line directly to this one, then the what is the state of the steam at 6 is, it is dry saturated. X is 1, dryness fraction is 1. And one more thing you remember, we are not going to supply the dry steam to the turbines. Okay, because still it contains a certain amount of the moisture. Okay, so suppose if you supply that dry steam to the turbine, so there will be a spoiling of the turbine blades, thereby decreasing the efficiency of the steam power plant. So always we have to supply the steam to the turbine. It is in the superheated state. You remember, superheated steam is the steam. We are going to heat the steam beyond the saturation temperature. When you heat the steam above 100 degrees Celsius, that is called as superheated steam. So there is always supply of superheated steam to the turbine blades, then only you will get the good efficiency. That's why that whatever 6 to 1 is represents the superheated state. Okay, 6 is your dry state. Exactly. And whatever here it is there, it is wet state. 6 to 1, up to 6 here it is dry state, and 6 to 1 is your superheated state. Okay, so these are the 6 points. You remember, 1 to 2 is your ideal expansion in the turbine. 2 to 3 is your constant temperature heat rejection in the condenser. 3 to 4 is your pump work, increase in the temperature and pressure. 4 to 5 is your regeneration work. 5 to 6 is your constant temperature heat addition, and then 6 to 1 is superheat. So whatever this diagram gives the ideal Rankine cycle, 1 2 3 4 5 6. Okay, and here QS means the heat supply takes place in the process 5 to 6, and heat rejection takes place in the process 2 to 3. Okay, and how to find out efficiency means, here it is turbine work, because expansion process takes place in turbine, compression process takes place in the pump. So we can tell it as WT minus WP divided by QS. Okay, net work is turbine work minus pump work divided by heat supplied. Turbine work is what I said, H1 minus H2. Okay, minus pump work is what, H4 minus H3. So H1 minus H2 minus of H4 minus H3 divided by heat supplied means what? Heat supplied means, as I said, H1 minus H3. So you have to neglect all these enthalpies. Okay, that is the ideal Rankine cycle. But in case of actual Rankine cycle, that is called as actual Vapour power cycle. You see the diagram. Okay, so whatever I explained till now, it is of ideal cycle. Now actual means, actual there will be some deviation from 1 to 2 to 1 to 2 dash. How we studied in turbine and compressor efficiency in gas power cycle, here also we are having some deviation, that is 2 dash. represents your actual expansion. 1, 2, 3, 4, 5, 6, 1 is your ideal Rankine cycle. 1, 2 dash, 3, 4, 4 dash, 5, 6, 1 is your actual Rankine cycle or actual Vapour power cycle. So very simple, just you have to add 1 point 2 dash, and then just you have to join with 1 2 dash and you draw the some line. Okay, so 2 dash 1 2 dash 3 4 4 dash 5 6 1 is your actual Vapour power cycle. And here 3 to 4 you can observe, this is called as pump work, where temperature and pressure increases. Okay, whatever the water coming out from the condenser, it gets pumped into the boiler. So 3 to 4 is your ideal pump work. On the other hand, there will be some deviation. You can see the point 4 dash 3 4 dash is your actual pump work. So by analyzing this TS diagram, we can say that 1 2 3 4 5 6 1 is your ideal Vapour power cycle. 1 2 dash 3 4 dash, you see the diagram, 1 2 dash 3 4 dash 5 6 1 is your actual Vapour power cycle. Okay, first drawing of TS diagram is most important. First you draw this diagram carefully, then after that you have to add the points. First you draw always ideal cycle. 1 2 3 4 5 6 1 is your ideal cycle. 1 2 dash 3 4 dash, okay, don't take 4 dash, actual 5 6 1 is your the actual Vapour power cycle. Then I'll tell process once again. 1 to 2 is your ideal expansion, and 1 2 dash is your actual expansion. 2 3 is your heat rejection in the condenser. 3 4 is your ideal pump work. 3 4 dash is your actual, where a dotted is there, no, that you take it as actual. 3 4 dash is actual pump work. Next 4 dash 5 is your regeneration work, and 5 to 6 is your isothermal heat addition, and 6 to 1 is your superheating. Superheating means increasing the temperature of the steam below the saturation temperature, and the cycle follows. So 1 2 dash is actual expansion. 2 dash 3 is your the heat rejection in the condenser at constant temperature. 3 4 is your ideal compression in the pump. 3 4 dash is your actual compression in the pump. 4 5 is your regeneration work. 5 6 is your the constant temperature heat addition. Okay, so next 6 to 1 is your the superheating, that is heating of the steam. You remember the condition of the steam at 6 is your dry state. So we have to supply the heat to increase the temperature of the steam. So we'll get the superheated steam. This is how to draw the actual and ideal Vapour power cycle or Rankine cycle. Rankine cycle is also called as Vapour power cycle. You remember, in case of Vapour cycle, we are having only two cycles. One is Carnot and one is Rankine. Carnot is not used because of its drawbacks. So we are going to use only Rankine cycle in steam power plants. One is ideal cycle and one is the actual cycle. Okay. Then what is the definition of your turbine efficiency and pump efficiency? How we are having compressor efficiency and turbine efficiency in gas power cycle? Same thing here also. Okay. How we are going to define the turbine efficiency is that we have to take actual turbine work, okay, divided by the ideal turbine work. So you have see this diagram, see this part, actual turbine work divided by the ideal turbine work. Actual turbine work is always you have to express in terms of enthalpy drop. You remember, we are going to concentrate mainly on temperature, enthalpy and entropy. Only these parameters. Pressure and volume does not comes into picture in Vapour power cycle because it mainly deals with heat and temperature and entropy. Okay. So actual turbine work is H1 minus H2 dash divided by H1 minus H2. Okay, less divided by higher value. Here H1 minus H2 divided by H1 minus H2. So we can define the turbine efficiency as the actual enthalpy drop or actual turbine work divided by ideal turbine work. Actual turbine work is H1 minus H2 dash divided by ideal is H1 minus H2. Now this is mainly related to your turbine efficiency. Then how we are going to define the pump efficiency? So in case of gas turbine cycle, we are having compressor, but here we don't have compressor. Instead of compressor, pump is used in place of compressor to increase the temperature and pressure. Okay. So how to define the pump efficiency? So here we have to take the less divided by higher value. Less is, we can define it as the ideal pump work, that is H4 minus H3 divided by actual pump work, that is H4 dash minus H3. Okay, so you have to remember these two formula to find out the turbine efficiency and pump efficiency in Vapour power cycle. Before that, first you have to analyze ideal Rankine cycle, actual Rankine cycle. Once you analyze this one, then you have to define the turbine efficiency. Turbine efficiency is what? Actual turbine work divided by ideal turbine work. H1 minus H2 dash divided by H1 minus H2. And in case of pump work, you have to take reverse way. First you have to take isentropic, means ideal you have to take. Okay, ideal as a numerator and ideal as a denominator in turbine. You remember the ideal work is the denominator in turbine, ideal work is the numerator in the pump work. So how we are going to define the ideal pump work? Ideal pump work is H4 minus H3 divided by the actual pump work is H4 dash minus H3. This is how to find out the turbine efficiency and pump efficiency. Okay. Guys, understanding pump efficiency and turbine efficiency? Any doubts?
No doubt, sir.
Okay, I'll continue. So next, because once you understand this concept, then remaining thing will be very easy to understand. Okay, that's why I'm concentrating more on ideal and actual and how to define turbine work and compressor work, turbine efficiency and compressor efficiency. Okay, next I'm going to discuss one important concept called as ideal regenerative Rankine cycle. Okay, so every time they used to ask this question for 10 marks, explain ideal regenerative Rankine cycle with flow diagram and TS diagram. Okay, you remember we have to draw only TS diagram in a Vapour power cycle. Okay, so before that I'll explain what you mean by the regenerative cycle. Okay, and in case of Rankine cycle, first I'll show the Rankine cycle flow, this one diagram. Okay, this is the Rankine cycle. Okay, this is the TS diagram of Rankine cycle and this is the flow diagram of Rankine cycle. Okay, so here first the whatever the steam generated from the boiler enters into the turbine. Okay, from the turbine the expansion takes place, then turbine it enters into the condenser, and then where condensation generates. Okay, and that condensate or water from the condenser enters into the pump, and then from the pump it enters into the boiler. Okay, this is what we studied. Okay, so actually the whatever the water or condensate coming from the condenser, it is pumped into the boiler. So here I shown one part is there, that is called as regeneration. Okay, regeneration means without supplying the water coming out from the pump directly into the boiler, we are going to heat that water to certain temperature, and that temperature is very low. Okay, suppose if you supply very less heat to the water, in that case the temperature will not increase much better. We have to increase the efficiency of the plant by means we have to add some more heat to the water, so then only we'll get the good efficiency. Here regenerator is there very less amount of the heat is supplied in the regenerator, that is called as feed heater. Suppose if you supply very less heat, in that case it is not sufficient to heat the water to the suitable temperature. In that case, what option is that in case of ideal regenerative cycle, we are having a part called as casing. Okay, so you see the diagram, casing is there around the turbine. Okay, in the turbine, so what is there, the vapor is there. Okay, and we are having the turbine casing, or it is also called as annular spacing, means certain tubes are present in the around the turbine this one structure, and in that annular spacing, so that water flows. Okay, so what we are going to do, so whatever water in the steam turbine, the steam flows, and in the surrounding tubes water flows, it acts as a heat exchanger. Suppose you provide some space between turbine and casing, that acts as a annular spacing where the water flows, so that water comes in contact with the steam. So whenever the water comes in contact with the steam, so that there will be exchange of the heat takes place, so that water gets heated. Okay, like that we can utilize that heated water to the entry of the turbine. Okay, remember one addition structure is there, that is called as annular spacing. Okay, annular spacing, or it is a circular tube where the water flows. Okay, in turbine the steam flows, and in the circular surrounding tubes the water flows. So water comes in contact with the steam, the heat exchange takes place, and whatever the water which is flowing around the turbine, it takes the heat from the steam, thereby gets heated up. That steam is taken in the cycle. Okay, first you see the what is the difference between your normal Rankine cycle and regeneration Rankine cycle is that just you have to show one circular tube. Okay, that is the difference, and remaining process is same. Okay, and I'll explain the TS diagram. Okay, and one, suppose if these tubings are not there, simple Rankine cycle, as I said, 1 2 3 4 4 dash and 1. Okay, so here this is your simple Rankine cycle. This is simple Rankine cycle. And ideal regenerative cycle, what happens? Okay, first I'll explain the procedure, and here you have to show these parts. Okay, first turbine, next from the turbine it enters into the condenser, from the condenser it enters into the pump, and in a normal cycle, so directly it enters into the boiler, but here it is not like that. So it does not enters into the boiler directly, rather than whatever the water coming out from the condenser is pumped into the turbine casing, you remember, in case of the regenerative cycle. But in normal cycle, you see the difference between normal cycle and regenerative cycle. Okay, in normal cycle, we are having 4 parts. So after coming out from the condenser, the water is pumped from condenser to boiler. But in case of regenerator, the water does not pumped into the boiler, rather than it enters into the turbine casing. Okay, I'll show this. You see you observe the difference between this diagram and whatever the diagram I am showing. This is the regenerative cycle. Instead of pumping the water from condenser into the boiler, it enters into the turbine casing. Okay, turbine casing where the water flows, it gets the heat from steam coming out from the turbine, gets heated. So instead of supplying directly from the condenser to boiler, first it enters into the turbine casing. Okay, this is the difference between normal Rankine cycle and it is a regenerative Rankine cycle. Okay, so next see 1 2 3 4 4-1 is your normal Rankine cycle. But in regenerative Rankine cycle, the process differs. Okay, you see, you have to start from 1 to 2 dash. 3, 4, 4 dash and 1. Okay, you have to take 1, 2 dash, 3, 4, and then 4 dash. Okay, so it enters like that. You have to take 4 dash and then 1. Okay, so 1, 2, 3, 4, 4 dash 1, 1, 2, 1, 2, 1, 2, 3, 4, 4 dash 1 is your normal Rankine cycle. When you are having the turbine casing, in that case, 1, 2 dash is your the entry of water from the boiler. Then 2 dash 3 is your condensation process. 3 to 4 is your pumping work. You see, remember 4 to 1 is most important. 4 to 4 dash here you have to take 4 to 4 dash here because it is a casing. 4 to 4 dash is your called as regeneration work. We are having 4 to 4 dash. 4 to 4 dash is called as regeneration work. Okay, then 4 dash 1. Okay, this is the cycle you have to represent. And here 1, 2, 3, 4, 4 dash 1 is simple Rankine cycle. When you are going to introduce the turbine casing or turbine cover, certain amount of the heat transfer takes place. In that case, you have to draw the diagram like this. So you have to add one line, 1, 2, and you have to drop here. This curve you have to add. So only, and you have to draw that line parallel to this line. First you draw 1, 2, 3, 4 normal Rankine cycle you draw. After that, you have to draw a line, whatever the exact 4, 4 dash, you draw a line parallel to this line. Then 4, 3 line parallel to this line. Just you draw whatever these two lines are there, just you draw two parallel lines here. Okay, that is your regenerative cycle. First you draw ideal regenerative cycle. After that, whatever this 4, 4 dash 3 is there, no, just you have to draw one line. You draw a line parallel to 4, 4 dash like this. Next, you draw one parallel line to 4, 3. Okay, this line parallel to 4, 3, and whatever line I'm showing, this line is parallel to 4, 4 dash in case of regenerative cycle. Okay, so this is how to draw regenerative cycle. First you draw 1, 2, 3, 4, 4 dash 1 is your ideal Rankine cycle. How to add your regenerative means just you have to draw a line parallel to 4, 4 dash, and then 4, 2, 3 is there, no, just you drop that one. Okay, so next you mark that point as 2 dash. Here it is there. Okay, then how the working of regenerative takes place. Okay, and I'll explain the working principle. Okay, in case of ideal, you remember it is ideal, not actual regenerative cycle. First I am explaining the ideal, and further I'll explain the practical or actual regenerative cycle. Regeneration means just you have to add the turbine casing. In the turbine casing, water flows, and that comes in contact with the steam. Okay, whenever the water comes in contact with the steam, the heat transfer takes place between the water and steam, and whatever that heated water directly enters into the turbine. That is a concept behind regenerative cycle. Okay, now I explain the working principle of ideal regenerative cycle. Okay. Okay, in the ideal regenerative cycle, so you know condensation happens in condenser where the vapor phase is converted into the liquid phase. The whatever the condense, you see the diagram 2-3. 2-3 is what your condensation. Condensation means what? That heat rejection means there will be change in phase from vapor to liquid. 2-3 is your condenser. Okay, so whatever the condensate coming out from the condenser, it is pumped. You see the structure pump. After passing through the condenser, it enters into the pump. So here it is gets pumped. What is the pump work? It increases the pressure. Okay, so that pump, this one liquid from the pump, and that enters into the annular spacing. You remember in case of normal cycle, after passing through the pump, it directly enters into the boiler, but it is not like that. Okay, so after passing through the pump, it enters into the turbine case. Okay, here remember it is what? condition is water. Okay, and here in the turbine, we are having the steam as a working fluid. Okay, the whatever the condensate coming out from the pump, rather than passing through the boiler directly, so it enters into the circular, okay, that is annular spacing in the turbine. Here this is the water, okay, and it comes in contact with the vapor. We know that in case of steam turbine, working fluid is steam. So this water, whatever it is coming out from the condenser, it gets exchanged with the steam. Okay, so when the water in the surrounding area comes in contact with the steam, it gets heated up. Okay, that outward is 4 dash. Inward you take it as 4, and outward you take it as 4 dash. 4 dash is your the regenerative work. You see, 4 dash, 4 and 4 dash. This is your circular structure or annular spacing. Take the entry as 4 and exit as 4 dash. Okay, and then that 4 dash, 2 dash 3 is your condensate work, 3 to 4 is your pump work, then 4 to 4 dash is your the regenerative work. What is the regenerative work? The whatever the water from the pump enters into the turbine spacing, it gets exchanged with the steam, thereby increasing the temperature. That water, whatever coming out from this turbine, once again enters into the boiler. Okay, here instead of entering from the pump directly, first it enters into the turbine annular spacing, where it gets exchanged with the steam which is flowing in the turbine. Okay, thereby increasing the temperature. That increased temperature of water then enters into the boiler. So instead of supplying the cold water directly from the pump into the boiler, first in regenerative Rankine cycle, first it made to pass through the annular spacing, thereby increasing the temperature, and then that state of the water is taken to the boiler, and then from the boiler it enters into the turbine. Hence the cycle repeats. Okay, you remember, just you have to show this annular spacing and you have to draw the TS diagram accordingly. Okay, so once again I'll explain the TS diagram. 1 2, first you draw ideal Rankine cycle. 1 2 3 4 4-1, it is your ideal Rankine cycle. How to add the regenerative Rankine cycle means, just you draw a line parallel to 4 4- and a draw line parallel to 4 3. Okay, this is how to draw a regenerative Rankine cycle, and just you drop a line. This is your S1, means the x coordinate indicates your entropy. So this one is S1, and this one is S2-, this one is your S4-, and this one is your S3. And here in the y coordinate it is T3, T4, T4-. Okay, so in the x coordinate, S3 and S4- are same. This is S4-, and this is S2-, and this is S1 and S2 are same. This is how to write the ideal and regenerative cycle. So this flow diagram is most important. I'll explain the working principle once again. The water, you start with condenser. Okay, whatever the steam coming out from the turbine enters into the condenser. As it enters into the condenser, temperature drops. There will be a change in phase from vapor to liquid. So the state is liquid here. That water, liquid state, enters into the pump. As it enters into the pump, the pressure increased. That water then enters into the annular spacing. Okay, instead of passing through the boiler directly, first it enters into the turbine casing. Here is water, and inside one it is steam. So this water, the mix gets exchange the heat with the steam, thereby increasing the temperature of the water. Okay, instead of supplying that cold water directly to the boiler, first it enters into the turbine covering, where it exchanges the heat, thereby increasing the temperature of the water, so that high temperature water from 4 dash then enters into the boiler. Okay, what is the boiler? Function of the boiler is to convert the water into the steam at a constant pressure. Okay, so that steam, whatever the steam generated in the boiler, then enters into the turbine for further expansion. Okay, I can tell 1 to 2 dash is your 1 to 2 dash is your expansion work in the turbine. 2 dash 3 is your condensation work in the condenser. 3 to 4 is your pump work. And you remember 4 to 4 dash, 4 to 4 dash, it is most important. 4 to 4 dash is your regenerative work. And 4 dash 1 is what? 4 dash 1 is your the constant temperature heat addition. Okay, so like that we are having the process. Then how to find out the efficiency? Very simple formula is there to find out the efficiency. Okay, so before, what is the efficiency? The heat supplied minus heat rejected divided by heat supplied. Already we derived in all the cycles. What is the heat supplied here? Okay, H1 heat supplied is your, where here we are going to express in terms of difference in temperature and this one. Okay, that is heat supplied is T1 into S1 minus S4 dash. You see, T1 into S1 minus S4 dash, that is called as heat supplied. Okay, T1 into S1 minus S4 dash. Okay, T1 into S1 minus S4 dash is your the heat supply, whatever the area under curve 1 4 dash. T1 into S1 minus S4 dash. So what about your heat rejection? That is T2 into S2 minus S3. Okay, so heat supplied is during process 1 4 dash, heat rejected is during process 2 3 dash. So heat supplied is T1 into S1 minus S4 dash. Heat rejection between the process 2 to 3 dash is your temperature T2. Okay, this T into S2 dash minus S3, you remember. So how we are getting the heat supplied and heat, you studied the formula. Entropy is given by what? Delta S equals to Q by T. So Q equals to delta S into T. Same formula you are applying. So Q is T into delta S. So heat supplied is T1 into S1 minus S4 dash. And then QR equals to T2. You see, these are all having same temperature. So T2 into S2 dash minus S3. That is your the amount of heat rejection. Okay. And this is the formula. Then here you see the diagram. The lines 4 4 dash and this line are parallel to each other. Okay, so we can have whatever S1 minus S4 dash is S1 minus S4 dash is exactly equals to S2 dash minus S3. Okay, so you see, because this line and this line is parallel, so S1 minus S4 dash is exactly equals to S2 dash minus S3 because of the nature of the diagram. Okay, QS is T1 into S1 minus S4 dash, QR equals to T2 into S2 dash minus S3. So because of the nature of the diagram, we can write S1 minus S4 dash is exactly equals to S2 dash minus S3 because of the parallel lines. Okay, now you see the very simple equation. Okay, only one line is there. Okay, so you have to substitute the value. Okay, QR by QS. What is QR? T2 into S2 dash minus S3, and QS is T1 into S1 minus S4 dash. From the diagram, so this S2 dash minus S2 dash minus S3 divided by S1 minus S4 dash. This is the ratio of QR by QS. But S1 minus S4 dash, you see the denominator, it is exactly equals to S2 dash minus S3. Both are same. Okay, so first you know QR and QS. QR is what? T2 into S2 dash minus S3 divided by QS is T1 into S1 minus S4 dash. Here S1 minus S4 dash and S2 dash minus S3 are the same because of the parallel line. So this S2 dash minus S3 and S1 minus S4 are same because of the parallel lines. These two gets cancelled. So QR by QS is T2 by T1. Okay. So QR, we know that what is the efficiency formula? So 1 minus QR by QS. How we are getting this one? Efficiency is QR minus QS divided by QS, or you can write 1 minus QR by QS. And ratio what we are getting is T2 by T1. So 1 minus T2 by T1. After simplifying, you are getting very simple equation 1 minus T2 by T1. So what is T2 by T1? It is nothing but your Carnot cycle efficiency. Hence, we can say that the efficiency of ideal regenerative cycle is exactly equals to your Carnot cycle. Okay. So because T1 minus T2 by T1 is your expression for Carnot cycle. Here also we are getting the efficiency as 1 minus T2 by T1. So whatever equation we are getting, it is exactly similar to your Carnot cycle efficiency. Okay, this is how to first you draw the flow diagram, next TS diagram, next 4 lines for finding out the efficiency. This is how to get the efficiency of ideal regenerative cycle. Okay. So understood, Tarun? Tarun Pachori?
Yes, sir.
Understood the derivation, how to take?
Yes, sir.
Okay, good. Chinmay Prasad?
Yes, sir.
Okay. No doubts? Any doubts? Any
No
point?
doubt, sir.
Good. Okay. Jayant Reddy? Uh, okay. Jayant Reddy? Good, Jayant Reddy. Okay, hope you understood the concept. That is, in this class, we discussed ideal regenerative cycle, flow diagram, TS diagram, and the efficiency is exactly same as that of your the Carnot cycle. That is T1 minus T2 divided by T1. That is similar to your Carnot cycle efficiency. So in the next class, I'll discuss the practical regenerative Rankine cycle. Today we discussed ideal. So in the tomorrow class, I'll discuss actual actual regenerative Rankine cycle. Okay. Thanks for joining this class. Okay.